Algebra 2 students, this is the daily lesson video for Friday, February 5th, where we will finish up section 6.1 with this main objective of finding nth roots. And what we spent yesterday doing was just talking about this numerically, just the numbers. If you just had to find nth roots of numbers, what would happen? And one of the things that happened was we came upon part C of the got it problem. And it was interesting because this was the only one that seemed to have math that had to be done before we could go ahead and take the square root. Because we had to treat that radical symbol, that square root symbol, as a grouping symbol. And that means everything underneath it has to be done first. So we went ahead and made -7 times -7, which is -7 squared, 49. And the square root of 49 is 7. And that was because these problems already had the square root symbols in them, or the cubed root, whatever it was, the radical symbols in them. And that meant we could just give principal root. So like it says, looking at part C of the got it problem, we see that if n is even, so this is our little imaginary 2 right there, then the nth root of a to the n is positive, even if a itself is negative. So here's what they're saying. This was a negative number. Square roots and squarings are supposed to be inverses of each other. So why couldn't we just drop the 2's and say the answer is -7? Because it doesn't work that way. We have to follow the order of operations. Always, we follow the order of operations. Now, we see a property here, and what they're getting at is that we're not just going to work with numbers anymore. We're also going to start seeing some variables. So this take note property of nth roots of nth powers says for any real number a, the nth root of a to the n if n is odd. So we've got cubed root of a to the third. Well, that's just going to give you a right back. But if the absolute value, if n is even, we have to have the absolute value of a. Now, the real reason behind this, why we suddenly need these absolute value bars, is this question right here. What did the author intend? The person that wrote the problem, did they mean for there to be negative answers when we were done with the problem? And all of that comes from what steps we're going to use inside the problem. So let's take a peek at some of these. Remember this rule. Watch closely when the radicand contains a variable expression. So if we have x's, y's, z's, whatever it may be, we have to include an absolute value when n is even. So that means we only need to worry about this if we're taking an even root. And you must omit it when n is odd. Now there's even better news, and that is sometimes we will have an even root, but we won't need the absolute value bars. So remember this rule. Watch closely when the radicand contains a variable expression. You must include the absolute value when n is even, and you must omit it when n is odd. So I'm going to talk you through this process, and then what we'll do is we'll write down something that a lot of students just memorize for this particular unit, for the absolute value part. And this says we're going to be simplifying radical expressions. What is a simpler form of each radical expression? Now, we have the square root of 16 and the square root of x to the 8th. We think of numbers differently than we think of variables when we're taking roots. So what we will want to do is split this into the square root of 16 and the square root of x to the 8th. And we want to think about the fact that if we have an x squared, to undo that, we would take the square root. And that would give us x. So in this case, if this is a square root, I'm going to find the square root of 16, which we all know what it is already. But then what I'm going to do is I'm going to make sure that I break up that x to the 8th into perfect squares. X squared, x squared, x squared, and x squared. And that uses the fact that when you multiply similar bases, you are supposed to add the exponents. So we have 2, 4, 6, 8. It says exactly the same thing as the square root of 16 and the square root of x to the 8th. And that says exactly the same thing as the square root of 16x to the 8th, because square roots can be multiplied by other square roots. So now, thinking back to what I want to do, I realize that's definitely a 4, square root of 16. And each of these is definitely an x. And make sure you use parentheses for that multiplication. In the Algebra 2 level, we are never using x to stand for multiplication. X is a variable. And now, if I have x to the first 4 times, when you multiply similar bases, you add the exponents, and I'll have 4x to the 4th. What they brought up is this absolute value thing. And they said, if you have an even index, which this problem does, our little index here, that's a 2. If you have a 2 there, you have to figure out whether or not the person that wrote this problem ever wanted there to be negative answers. And if they did, well, then you don't have to have absolute value bars. But if they didn't, well, then you have to put the absolute value bars in there. So I look at the problem 2 ways. First, I start underneath it. If I were to put a number in this, and think of it as a negative number that you're going to put in, and raise it to the 8th power, there was never a chance that that was going to come out to be negative. And if that's the case, then, unless my answer already takes care of that and makes sure there's never going to be any negatives, I'm going to need absolute value bars. So now I go down to my answer. If I were to put a negative number in for x and raise it to the 4th power, is there ever a possibility that it would be negative? And the answer is no, because we're raising it to the 4th power. So my answer is fine as it is, and it does not need absolute value bars. What the author wanted was always positive answers. That's what they wanted, no matter what, because they had an x to the 8th in there. And my answer of x to the 4th is going to do the same thing. Now, like I said, that's the way you should truly think about this. But that's kind of hard for some Algebra 2 students to figure out, well, what did the author want, and go through that. So there is an easy little, sentence that people always think of when they're doing absolute value, and that is even index, odd power answer needs absolute value. And quite honestly, most people just do even index, odd power answer. Because an even index can only be used when we're taking the square root of positive values. So if the author allowed that, well, then we have to look into whether or not our answer, what we simplified the problem to, would do the same thing. So even index, odd power answers, you have to have the absolute value bars. But no, this is only for variables. That's why we didn't talk about this yesterday. Only for variables. So I'm looking at B, and I realize I don't even need to think about the absolute value piece with that one, because that's going to be a cube root. That's odd. If I go back to A and I say, hey, this had an even index, did my answer come out with an odd power? Oh, no, it didn't. It was even. So that's why I didn't need absolute value bars. Back to B, we would split this up as the cubed root of a to the 6th and the cubed root of b to the 9th, and then split it again, because right there, if you multiplied those back together, that would be the cubed root of a to the 6th, because when we multiply similar bases, we add the exponents. And then we'll do the same thing with the b's. B to the third, B to the third, B to the third. That's 9 of them. And that will give us A times B times B times B. And now we'll collect them back up. A times A is A squared. B times B times B. B to the third. And again, at the end, I want to think, well, do I need absolute value bars? No, because this one had an odd index. Let's go to C. C has the fourth root of x to the 8th, y to the 12th. Again, I make my index match my powers. We start with the fourth root of x to the 8th and the fourth root of y to the 12th to separate our variables. And then the fourth root of x to the 4th, fourth root of x to the 4th, because together that gives us x to the 8th. Fourth root of y to the 4th, fourth root of y to the 4th, fourth root of y to the 4th, so that we have 4 plus 4 plus 4, which is 12. And this would be x times y times y times y, which is x squared y to the third. Now, this was an even root, an even index. So I have to check and see, did the author ever want a negative answer to come out of this? And as I go back to the original, I realize, no, they didn't want a negative answer coming out because they're raising x to the 8th power and y to the 12th power. Everything that comes out of their formula would come out positive. But look at our answer. That's not true with our answer. Whatever we put in for x would be fine because we're going to square it, but not y because that's to the 3rd power. So I have to put absolute value bars around that y to keep the author's intent. Now, if you like the shortcut, well, then this goes a lot faster because you can look at it and say, even root, 3 is an odd power answer. That's going to need the absolute value bars. So, like I said, we'd prefer everybody thinks of it as the author's intent, but if you need a fast and easy way to memorize it, you can just memorize even root that comes out with an odd power answer, remembering that that's variables only. All right, 3a, what is the simplified form of each radical expression? Let's separate that into the square root of 81, the square root of x to the 4th, and then the square root of x to the 4th, we'll make that the square root of x squared times the square root of x squared. Square root of 81 is 9. Square root of x squared is x. Multiply it back together. And now ask yourself if you need absolute value bars. Well, this was a 2. So it does have an even root. So if we have an odd power for an answer for our x, we're going to need absolute value bars. We don't. It's squared, so this is perfectly fine. Doesn't need absolute value bars. Again, if you think about it as author's intent, there's no way that was ever going to be negative. Any number put in there for x was raised to the 4th power, which would make it positive. And our answer makes sure as well that that will always be positive because it's going to be squared. So it doesn't require absolute value bars. B, cube root. Break it apart into those variables. Cubed root of a to the 12th, cubed root of b to the 15th. And now make your perfect cubes. So cubed root of a to the 3rd, cubed root of a to the 3rd, cubed root of a to the 3rd, cubed root of a to the 3rd. 3, 6, 9, 12 of them. Cubed root of b to the 3rd, 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 cubed root of b to the 3rd. Well, we'll have a times a times a times a. And then we'll have b times b times b times b times b. And that will give us a to the 4th, b to the 5th. Now at this point, when we're in class together, I will usually ask if anybody has noted the shortcut way So as you were going through this, you noticed something and said, oh, well, I could just do this. And that this is going to be using division. So far, all of these that we've done, if we take 3 and divide it by 12, we get 4. If we take 15 and divide it by 3, we get 5. If we take 4 and divide it by 2, we get 2. So the ones that we've had so far were perfect because they were always divisible by what we had for our index. So if you notice that, you can certainly use that instead of writing them out by expansion, which is what I'm doing. And the reason that I do that is because over the years, 20 years of teaching Algebra 2, this is the way that most students will understand it. If I say division, well, then I'm asking them to memorize, and that doesn't usually work out well. The logic behind the expansion usually helps students figure out why things work the way that they do and makes it understandable. So for C, I should go back to B for a second. Remember that that was cubed roots, so that does not need absolute value bars, only even roots. All right, so now we have a fourth root. And let's just say we noticed that pattern. So 4 goes into 12 3 times, and 4 goes into 16 4 times. And then we memorized even roots with odd power answers need absolute value. Well, this is an even root. It's a 4. And the x variable came out with an odd power answer. So that needs our absolute value bars. All right. Now, problem 4 is still with our objective, but what it's doing is it's doing a word problem and talking about our radical expressions. So, big chunk of what we learned today had to do with figuring out what to do with those variables, and then when do we need absolute value bars. So even roots with odd power answers get our absolute value bars. Problem 4 says using a radical expression. Academics. Some teachers adjust test scores when a test is difficult. One teacher's formula for adjusting scores is A equals 10 square roots of R, where A is the adjusted score, so the one they actually put in the grade book, and R is the raw score, the one that's when the teacher first graded it was on the paper. If the raw scores on one test range from 36 to 90, what's the range of the adjusted scores? Well, let's see. What happens to that 36 when it goes in the formula for R? And what happens to that 90 when it goes in for R? Well, this one would just be 10 times 6. So that's pretty good for somebody who only scored a 36 on their test. They're going to get a 60 in the grade book. Then for the second one, we need to see what 10 times the square root of 90 is, and that's not a perfect square. So we'd grab a calculator and punch that in, and it's about 94.87. So the person with the 90, they got a little bit of a boost at 4.87. And these squiggly equals, those mean approximately. So approximately 94.87 because I had to round. So if the scores were from 36 to 90 for raw scores, the adjusted scores range from 60 to approximately 94.87. Because I wanted to word it the way that they asked the question. So if we go back up to the problem, we see that their question was, what is the range of the adjusted scores? So the adjusted scores range from 60 to approximately 94.87. So if they give us raw scores, we put those numbers in for R. If they give us adjusted scores, we put those in for A. In problem 4, what are the adjusted scores for raw scores from 0 to 100? All right, so this time we're going to put in a 0 for a raw score, and we're going to put in a 100 for a raw score. Well, the square root of 0 is 0, and 10 times 0 is 0. The square root of 100 is 10. So if you have a score of 0, somebody didn't even take the test, and if you have a perfect paper, well, then the range of scores stays from 0 to 100. So we had best say that. The adjusted scores will range from 0 to 100. So they're just showing us that, if somebody is going to curve a test, that's what people always ask. Is there a curve? Well, first of all, there's never a curve in Algebra 2 because we write our tests so that the students that understand truly everything can get 100%, and then anywhere all the way down to 0, of course, for the percentages. So there are some teachers that curve, just not going to be in the math department. And the reason that they do it is to give students that truly struggle a chance of actually passing the course, because a lot of schools used to have a passing rate of 60%. And then it was thought, well, 60%, that's not enough. If somebody's going to pass, they should know more than 60%. So it got argued up to 65%. So there are a lot of different philosophies and a lot of different ways that people grade out there. This would just be one of them. And then yesterday you did the assignment that's circled in red up there. Today, do the blue. So section 6.1 day 2, page 364, I shouldn't have written over the top of it. Numbers 10 through 28, the evens, 31, 33, and then 65 to 67. And next week we will start on section 6.2. So have a good weekend, everybody.